Welcome everyone to today's Explainer. I'm really excited to dive into this one with you. Imagine, for a second, a world right after the catastrophic event that wiped out the dinosaurs. The forests had collapsed, food chains were completely broken, and yet, in the incredibly warm world that was left behind, something truly unbelievable slithered its way to the top of the food chain. Today, we're going to examine how a 66-million-year-old fossil anomaly completely reshaped our understanding of prehistoric tropical ecosystems, and we'll look at the exact hard-won evidence that allowed us researchers to reconstruct this ancient beast.
Here is a quick look at what we'll be covering in our explainer today. We're going to start with the Paleocene ecosystem anomaly. Then we'll get into the gritty reality of unearthing the La Puente Cut. From there, we'll break down the math behind reconstructing the monster, explore ectotherms and extreme heat, and finally wrap up with carbon echoes, then versus now.
All right, let's jump right into part one, the Paleocene ecosystem anomaly.
To truly understand an anomaly, you first need the right window into the past. Immediately following the dinosaur extinction, the Earth was this sweltering, swampy jungle. Now, for years, the fossil record really only showed a slow bounce-back period. We certainly weren't seeing any extreme gigantism. But as our esteemed colleague, paleobotanist Carlos Jaramillo brilliantly put it, the massive Cerrejón coal mine in Colombia inadvertently opened up a window into a complete ancient tropical ecosystem. Today, Cerrejón is just this enormous, dusty, open-pit coal operation that covers an area literally larger than the city of Chicago. But 60 million years ago, its lush, colossal vegetation decayed over millions of years to form the very coal we are mining today. So mining that coal is essentially peeling back the earth to reveal these buried secrets.
Which brings us to part two, unearthing La Puente Cut. Let's talk about the fieldwork. Making sense of this site was a decades-long puzzle for our investigative teams. Back in the 90s, we had this accidental discovery of fossilized leaves, found right alongside what we actually misidentified for years as a giant crocodilian jaw. Fast forward to 2007, a grad student named Alex Hastings was unwrapping a single enormous vertebra that we had sent back from the site. Again, we initially just assumed it was a crocodile bone, but when he compared it against the university collections, absolute shock. It wasn't a croc, it was a snake vertebra, and it was a staggering 3 times larger than that of a modern anaconda.
Now, I have to emphasize just how difficult it was to get those fossils into the lab in the first place. The specific 6,000-acre northern sector we were working in, known as the La Puente Cut, was an absolute nightmare. Our field teams were subjected to absolutely brutal conditions. We baked in extreme heat, well over 30 degrees Celsius, with literally zero vegetation for shade. We were constantly lashed by 40-kilometer-per-hour gusts of wind. We actually had to dodge spontaneous methane fires erupting right out of the coal seams. And on top of all that, we battled daily torrential rains that would completely erase our excavation progress from the day before. Every single bone we recovered out there was a hard-won victory.
Okay, part three, reconstructing the monster.
So here is the crucial question. How do you accurately size a giant snake when you only have a fraction of its spinal column? Snakes rarely fossilize completely because their bones are incredibly delicate, so we really had to get creative here. Researchers David Polly and Jason Head came up with this brilliantly elegant mathematical model. They realized that every individual bone in a living snake's spine corresponds to a very specific region on its back. By analyzing modern living species from the Boidae family, think boas and anacondas, they plotted each joint, ridge, and vertebrae as a strict set of geometric coordinates. By plugging our giant, T-shaped fossil vertebrae into this mathematical model, we could accurately extrapolate the creature's true terrifying scale.
And the result of those calculations? Staggering. It revealed a behemoth that measured up to 15 meters in length and weighed an average of 1,135 kilograms. To put that into perspective, that is heavier than a small car or a fully grown rhino. If this thing slithered past you, its back would come right up to your waist. We formally named it Titanoboa cerrejonensis in 2009. It is, without a doubt, the largest snake in Earth's history. But, while the math gave us its massive size, it didn't tell us how this monster actually lived. For that, we needed its head.
Finding a snake skull on the fossil record is like finding a needle in 1,000 haystacks. The bones aren't fused together, so they usually just decompose and scatter. But in 2011, we miraculously recovered 3 tiny skull fragments, and they completely cracked the code for us.
We found a shallow quadrant bone angle, which allowed the back of the lower jaw to extend far behind its brain, meaning it could open its mouth incredibly wide. Plus, its closely packed teeth were a dead giveaway for specialized fish hunting. Piecing all this together, we deduced this wasn't just some fast land-roaming constrictor dragging a ton of muscle through the dirt. No, this was a specialized, semi-aquatic apex predator. It likely lurked silently in dark, tannin-stained swamp waters, just waiting to ambush giant prey.
Moving on to part 4, ectotherms and extreme heat. Let's look at the biology.
You have to ask what kind of environmental conditions actually permit a reptile to achieve such immense gigantism. The key to this puzzle is that snakes are ectotherms. This means they depend entirely on the warmth of their surroundings for their bodily functions, so their physical size is strictly bottlenecked by ambient heat. The warmer the environment, the more energy they absorb, the faster their metabolism runs, and ultimately, the bigger they can physically grow. Titanoboa's massive scale wasn't just some random freak of nature. It was a direct biological thermometer for an extreme ancient world.
To verify this, we cross-referenced the snake's biology directly with the local flora, and the data we extracted from fossilized plant leaves found at Cerrejón confirmed our hypothesis perfectly. Studies of carbon isotopes and leaf pores showed that Titanoboa thrived in a relentless, sweaty sauna with year-round average temperatures hovering between 30 and 34 degrees Celsius. This scorching environment was driven by atmospheric carbon dioxide levels estimated to be 50% higher than they are today. That extreme heat is exactly what allowed cold-blooded giants, not just snakes, but turtles with shells the size of snooker tables and massive crocodilians, to utterly dominate the landscape.
Which brings us to our final section, part 5, carbon echoes, then versus now.
So what does this all mean for us? If the Earth was that hot back then and it supported this lush, highly productive forest, what happens as our modern greenhouse gases rise today? Well, the absolute critical difference here is timescale. The ancient climate warming of the Paleocene occurred very gradually, over millions of years. That gave those lush ecosystems, the robust plant life, and giant species like Titanoboa the evolutionary breathing room they needed to genetically adapt and thrive in that extreme heat. But modern climate change, it is occurring rapidly over mere centuries, and in some places, just decades. This hyper-accelerated shift is already causing immediate plant die-offs because species simply cannot adapt to the sudden shock.
I want to end our explainer today by leaving you with this thought. Look, the internet absolutely loves conspiracy theories about bus-sized snakes still hiding out deep in the modern Amazon. But the truth is, Titanoboa itself will not return because its highly specific, ultra-warm climate no longer exists. However, its fossilized bones remain our greatest, most tangible warning about the profound, world-altering power of shifting temperatures. As our modern climate rapidly shifts without giving life the millions of years it naturally needs to adjust, what extreme biological adaptations are we losing before they even have the chance to evolve? Thank you so much for joining me to explore this fascinating ecosystem anomaly today.